Good morning, everyone. This is John Pendleton, your trainer today, and we're going to cover some heat of extraction rejection calculations today. So we will go ahead and get started. Let me slide that control panel over. So this is me. I'm the trainer. I'm their senior trainer at Enertech. I've been with Enertech for it'll be 8 years at the end of the month. So started out in tech support, and I've been head trainer for the past, about a year or so now. So if you need anything from me as far as training information, or you've got any questions, you can call me at the 618-690-3275. Sorry about that. Let me want to make sure you guys could hear me there. Sorry about that. You can also call the 618-664-5860 number, and that will ring in back to technical support. So if you have any technical support questions, it'll ring back to the group of us. There's 4 of us back there, 5 of us, so you can call that number. You can also send me an email at john.pendleton@enertechgeo.com, or you can email at training@enertechgeo.com. Those both email accounts come to me. So if you got any questions, need some PowerPoints, anything, request some training, you can reach out to me. Today's webinar will be recorded and uploaded to our YouTube channel, which is Enertech University. It'll be uploaded there probably this afternoon, so you can go back and check it out. You can check out our past webinars as well. So heat of extraction, heat of rejection is what we're going to cover today, and it's the same calculation. We're just trying to figure out what kind of heat we're pulling out of the loop field, or what kind of heat we're taking from the home and putting into the loop field. And it'll basically tell us, compared to the numbers that are in the manual, how that unit is running. When we do heat of extraction and heat of rejection, there's no refrigerant gauges are needed, so you can just leave those on your truck for the time being. It basically verifies the equipment performance by measuring the amount of heat that's either being rejected or extracted from that loop field. Basically, you're going to need a water pressure gauge with a needle on it, usually a 0 to 100 psi, and a thermometer of some type. I would recommend digital on both the pressure and the temperature gauges. Some of the smaller units have some pretty small pressure drops to figure out our flow, and so it's a lot easier to see on a digital pressure gauge than it is with a analog type gauge. We do have we have a Dwyer digital pressure gauge that we offer. You can also go online and buy it. And then we also offer some digital thermometers too that are kind of tapered at one end that kind of go into those pressure temperature ports a little bit easier. And I believe it's a Cooper thermometer. That's a yellow one. You can get it online. You can order it from us. Again, it does go into those PT ports a lot easier because it is tapered and it's a lot smaller. So if you've ever used the older style thermometers, had the real wide shaft on it, you'd stick it in that PT port, didn't want to come out, and you'd pull on your thermometer and the head and wire would come out and the metal would still be stuck in there. So we found that these Cooper thermometers work really well. Basically, we've got to have the IOM information. So if you don't have an IOM when you're doing heat of extraction, give us a call on tech support. You can give us the numbers and we can look it up for you, or we can send you a PDF of the IOM or the spec manual. We've got to have pressure temperature ports on all of our units, and those are so we can access the water circuit and see what kind of flow you're moving, as well as get your temperature difference. Now, we could get temperature difference on the outside of a pipe. It may not be the exact true temperature of the water that's in the pipe, but it's going to be pretty close. If we need to figure out flow, the only way to establish flow is with pressure temperature ports. So we've got to make sure we're putting those in on every install. And if you've got a water-to-water unit, so you don't have like a forced air, you've got radiant zones, we're going to need those pressure temperature ports on the load side as well, because we've got to establish flow and see what kind of temperature difference we're exchanging on that heat exchanger as well. We would recommend that you do run the unit in second stage if it's a dual capacity unit. We do have a lot of numbers at part load in the manual, but we would always recommend that you run it in the Y2 second stage of the compressor. You can turn the desuperheater off, you can leave it on. Some of the manuals will have the heat of extraction, heat of rejection with the desuperheater on. Usually the desuperheater will rob, 3,000 to 5,000 BTUs from the total heat of extraction or rejection. So the first thing we've got to do is we've got to understand the engineering data tables in the manual. So we'll pull up here a manual. This is similar to what the ones in the manual now really break it down. This has 30-degree entering water temperature, and then it jumps to 50. In the newer manuals, we'll have 30, 35, 40, 45, 50. So it'll really bring you a lot closer into it. Basically, on the chart here, on the top of it, we have entering water temperature. Now, that entering water temperature is your entering source water temperature. So that's on your heat exchanger, your coax, or your braze plate, whichever you've got, but it's the source entering water. And hopefully you've got a PT port there, and we'll check that entering water. That kind of sets us a mark of where we need to look on this chart to start off with. The next is our flow rate. Now it'll show on the flow rate GPM, and then it says WPD, and that stands for water pressure drop. And we have that in PSI and feet ahead. We don't really worry about feet ahead too much. That feet ahead is kind of nice if you want to know how much feet ahead at 9 GPM at 30 degrees that heat exchanger has. So it's good if you're going to size a pump. That's what we use that feet ahead for, to make sure that pump can pump that amount of fluid through your circuit. So when we go to size a pump, we'll use that number. But normally we're going to use the PSI. That PSI is the pressure drop. So GPM and flow rate is basically the amount of gallons per minute that are flowing through that coax. So we're normally somewhere between 1.5 gallons per minute and 3 gallons per minute, depending on the type of system. And we'll cover that just a little bit later on. So we're going to use the PSI pressure drop. So if you take pressure in and pressure out and do the math on that, that's your pressure drop. If you ever have a lower pressure in than you do out, then you've got your flow reversed. Normally there's stickers on the cabinet that'll tell you what the source in and source out is, but there's been a few times when I've seen the factory get those stickers flip-flopped. And so if you think that it's swapped, look in the IOM. The IOM will tell you where the source in and source out should be, and then you can kind of compare it. I really wouldn't, worry about it too much, but I have seen it a couple times. That's one of the things at the factory that's kind of some human error could happen. So we've tried to take steps to remedy that, but it could occasionally happen. Not that it happens often, but I have seen it before. So if you take that pressure drop in and out, you can actually figure out, you have to have the manual with your pressure drop to tell you what the GPM is. You can't just say, I don't have a math calculation that says, okay, if I have 4 pounds of pressure drop at 30 degrees, is there an equation that I can figure out the GPM? The answer is no. You basically have to have the manual to tell you with that pressure drop what the GPM is. The next is our entering air temperature. We'll list some return air temperatures for you so you can kind of get a little bit closer to your heat of extraction. It won't really matter a whole lot, maybe a couple thousand BTUs, which I guess on a smaller unit, it could affect it. So you might want to take a look at that. And then also, if you are outside of, we usually have 60, 70, and 80 degree return air temperatures. If you're outside of those numbers, we do have a correction factor chart in the manual that you can use if your return temperatures are, outside of these ranges. But again, entering air is just that. It's the entering air on the return side is what we're looking at. So again, if we have 65 degrees, we can look at this little chart here and use some correction factors. To be honest, I've only used this correction factor chart just a couple times. Normally the calculation will work out okay, and we don't have to really worry about it too much. So you may or may not really need this chart. Heating capacity. So you can see, if you look at this chart here, you'll see HC and HE. HE is in the yellow there. You can say the HC, or heating capacity, of this unit is 30,200 BTUs. The heat of extraction is 21,700 at 21.7. So heating capacity is the total heating capacity of the unit. Heat of extraction is what we're taking out of the loop field. We have in the circuit what we call heat of compression. So that's basically the electrical circuit, the compressor that's going to produce heat, and we've got to do something with that heat. So heat of extraction is what we're extracting out of the loop field. The heat of compression, we have to pick up and do something with it as well. So in heating mode, we can use that for our heating capacity. So total heating capacity into the home is heat of extraction plus the heat of compression. In this example, we're just going to say that it's 10,000 BTUs in the refrigerant circuit on the compressor. So 30,000 from the loop field plus 10,000 from the heat of compression equals 40,000 BTUs total heating to the home. The heat of extraction, again, is just that. It's what we're pulling out of the loop field. And then heating capacity is with the heat of compression. We can actually figure out that how many BTUs that compressor is creating. BTUs, we can figure out BTUs, volts times amps equals watts. Watts times 3.41 equals BTUs. So in the field, it's easy to check amps with your amp meter and volts. So it's pretty simple to get that number. You just have to kind of remember volts times amps equals watts. Watts times 3.41 equals BTUs. So you can actually figure out your total heating capacity. Now, when I say that volts times amps equals watts times 3.41, that'll give you a number. Let's say it is 10,000 BTUs. The compressor is not 100% efficient, so you're going to lose a little bit of that heat. So usually a compressor is about 90% efficient. So we could take that 10,000 BTUs that we calculated, multiply that by 0.9, which will give us, in this example, 9,000 BTUs. So that would be what the compressor is actually generating as far as heat-wise. And if you've ever looked at heat of rejection and heat of extraction, you'll notice that heat of extraction is always lower than heat of rejection. In cooling mode, we're pulling heat from the home. We're also picking up that heat of compression in the compressor. We still have to do something with it, and we're putting that into the loop field as well. So if for some reason we were pulling 40,000 BTUs from the home, we would pick up that heat of compression, which would be 10,000 BTUs. And so you would put 50,000 BTUs back into the loop field. So heat of rejection should always be higher than your heat of extraction. Leaving air temp, that's your return air temp or your supply air temperature. Normally the supply air temperature is 20 to, or 20, 25, 30 degree temperature difference, depending on your airflow, is what we should be getting across that air coil. So if you see like, I don't know, maybe 15 degree temperature difference, make sure that the unit is in second stage, because it could be that it's not in the second stage, or obviously there could be an issue as well, but Normally we're somewhere right around the 25-degree temperature difference mark in second stage. Your input, that's in kilowatts. Again, that's your volts times amps right there. So it's BTUs converted to watts, which again is volts times amps equals watts times 3.41. That'll give you your kW, your kilowatts. COP is the efficiency of the unit, how efficient the unit is running. And if you ever have a homeowner complaining about high bills, again, this is a calculation that you can figure out in the field. Basically, energy delivered divided by the energy supplied. So in this example, if we have 30,000 from the loop field, we're picking up 10,000 BTUs and we're delivering 40,000 BTUs. So our energy delivered would be the 40,000. The energy supplied to create this is by the compressor, that 10,000 BTUs, that heat of compression. So in this example, we would take 40,000 and divide that by 10,000, and that gives us the 4.0 COP, coefficient of performance. In cooling mode, we use EER, but it's basically the same, roughly the same calculation, but we do not convert it over to BTUs. So again, energy delivered divided by energy supplied. So in this example here, we've got 21,000 BTUs, or excuse me, 30,200 BTUs being supplied, and we're delivering it with that 2.47 kilowatts converted to BTUs. In this example, it would tell us we've got a 3.58 COP is what we should have. Now, it doesn't necessarily mean that's what you're producing, but in the lab conditions, this is what our COP was. So it's a great way to check if a homeowner is complaining about high bills to actually see how efficient the unit is running compared to the engineering specs. So how do we perform the measurements and the calculations? So before a system can properly be diagnosed or serviced, we've got to make sure water flow and airflow are within specs. Now, airflow, if you've got an ECM blower motor, you can just look at the blinks on that ECM board, and for every one blink, that equals 100 CFM. Now, if you have, let's say you should be running 1740 CFM, it won't flash like a 17.5 flashes. It'll flash 17, give you a weird blink, letting you know it's getting ready to start over. But it'll get you in the ballpark of, you know, what your CFM should be. So you can count your CFM blinks and see what you're moving. Water flow, we've got to have either a flow meter or pressure drop. So we've got to make sure we've got water and airflow first before we can even expect the unit to operate properly. Obviously, the compressor has to be running, your pumps need to be running, and that kind of thing. So everything's got to be operational to a certain extent in order to be able to start checking heat of extraction or heat of rejection. Again, here is the Dwyer pressure gauge that I recommend. Now, if you buy it online, it will not come with this needle. But to be honest, it doesn't come with a needle when you buy it from Enertech either. But customer service is real good about asking you if you want to add that needle on there. Because I'd hate for you to get your gauge and have to go back and find the needle. Not that you can't get it, but just remember it doesn't come with it. The old style temperature gauge or temperature thermometer there, the black one's the old style. It's kind of got the thicker shaft on it. It will work. You may need to use some type of water soluble grease in there to be able to get it into the PT port without stretching it out. But as you can see, this Cooper on the bottom, it's got that real small tapered end, and it goes into those PT ports really nice. You won't have to use channel locks on it to get it back out. and they work really nice. They're replaceable batteries in them. I don't know, I think we maybe sell them for like 20, 25 bucks at Enertech, or they're roughly the same price online. So anytime you have a closed loop, well, any kind of water coming in, pumping down, open loop, pressurized, non-pressurized, always install pressure temperature ports. Basically, the outside is brass, then it's got a neoprene black gasket in there or seal that's got a little X cut into it, and it does have some threads and a cap. So over time, if you keep putting your temperature gauge into that PT port, it will kind of stretch it out, and it may start dripping and leaking. So that's what the caps are for, to seal it up. So over time, it will happen. It's not uncommon, not a big deal as long as you have the caps. If you don't have the caps, it's going to leak on the floor. You're going to lose pressure and that kind of thing. So make sure you got the caps. Make sure you're installing pressure temperature ports. Some tools needed to verify performance on a non-pressurized system. Now, the NP series, the newest composite cabinet, non-pressurized flow center. With that flow center, the pressure drop is accurate and you can use it for flow. If you've got the older QT style non-pressurized flow center, it's kind of a white cabinet. That one you have to have a flow meter to establish your flow. Basically, there's a dip tube inside of the tank. You've got some PVC with a flow meter on it. You hook it up into that PVC and dump the water back into the canister there. And there's a float on that flow meter tool that'll tell you how much GPM you're moving. So normally once you get that flow set, it shouldn't change. But if you've got a problem going on, we'll definitely want to check on that. Again, the white cabinet flow centers, you'll have to use the flow meter tool on it. Here is the heat of extraction, heat of rejection formula. Basically, TD is temperature difference, and that's between your entering and leaving water. Your GPM is your gallons per minute, but we get that by taking your PSI pressure drop converted to GPM using the ILM. Brine factor, it's found by multiplying the weight of the water times 60 minutes in an hour. That's really not that important. All you really need to know is if you've got a pure water, you're not using any type of antifreeze in the system, then it's 500 for the brine factor. And if you've got any type of antifreeze mixture, we use 485. Now there you can get the actual specific gravity of the fluid, but 485 will put you in a ballpark close enough for what we're doing. And it's an easy number to pretty much remember. 500 for pure water, 485 for an antifreeze mixture. Normally you're going to have antifreeze on a closed loop, unless maybe you're down in Florida, the Caribbean, or southern Texas or something like that. We put that antifreeze obviously in the water to prevent it from freezing. When we design loop fields, they normally design them for 30 degrees. Now, you say, well, it probably won't really freeze if it's moving at 30 degrees, and you're correct, but those are for design days. You know, we don't design a system when it's 0 out for a week straight. Now, maybe they do up in Canada, but they, here in the Midwest, no. You have to oversize your loop so much. So there will be times when we drop below that 30 degrees, maybe down to 25 or so, maybe down even to 20 degrees. And so we need to make sure we've got freeze protection for those non-degree days. So that's why we put the antifreeze in there. We know that there's going to be certain times when that loop field drops below and could freeze. So that's why we put the antifreeze in there. This is actually a specific gravity chart, or the capacity factor of the different types of antifreezes. So you can actually see propylene glycol at 30% is actually a 483, not 485, like I just told you. We've got ethanol methanol is 490. Water is not actually 500, it's 501, but for using it to remember, 45 and 500 will work for you most of the time. Sometimes when we get into the variable speed flow centers with the controller on it, it will use the exact specific gravity. So if you look at the screen on it and you do a hand calculation of your heat of extraction, those two numbers could be a little bit off from each other. And that's because that computer in that control module will use the exact capacity factor of that antifreeze type. So when we go back and look at the IOM, you'll see, let's say we're at 30 degree entering water temperature. You've got 6, 9, and 12 GPM. Well, you can't just say, well, I'm moving 9 because that's what I want. You can't just pick one. You'll have to look at your pressure drop, and that'll tell you what the GPM. But there are 3 flow rates represented. And the reason that there are is, like at 30, well, we'll look at, 30 degree entering water temperature. That first GPM is the minimum flow rate for an open loop. This is a 4-ton unit. So the minimum flow rate we want on an open loop is 1.5 GPM per ton. So 1.5 times 4 is 6. So we do that on an open loop because we're normally pulling from a well and dumping that water. And it's a very consistent 50 degree entering water temperature all the time. So we can use a lower water temperature and still keep our performance where we need it without running high pressures, that kind of thing. The next flow rate is the minimum flow rate for a closed loop system. So the minimum flow rate for that would be 2.25 GPM per ton. So 2.25 times 4 is 9 GPM. And then the last flow rate is the recommended flow rate for a closed loop system, which is 3 GPM per ton. Now, if you move more flow than what's listed, it's not the end of the world. You will waste a little bit of pumping watts, but the unit will still perform. Maybe not quite as efficient, but it'll still work. Basically, as you speed up the water flow, your temperature difference will get narrower or smaller. And that's basically because the water is in contact with the pipe for less amount of time, so it can transfer heat. It doesn't transfer heat quite as well. So as you slow down your water flow, obviously temperature difference increases. If we look at like an open loop, normally the temperature difference on that water could be like 15 degrees. If we've got recommended flow rate going through the system, you're doubling your flow rate. So you can imagine that your temperature difference is going to be cut in half. So is that 15 on an open loop, you'll probably be about 8 degrees on a closed loop. So you just have to kind of take that in consideration. The faster you move the water, the smaller the temperature difference will be. So here's a flow rate example, basically 30 degree entering water temperature. We've got PSI in is 40.8, PSI out is 36. So we just do the math on that, that'll be 4.8 pressure drop. If we looked on the YT unit, it would tell us at 30 degree entering water temperature, at a 4.8 pressure drop here, that's that number 3 would be 12 GPM. So that's how we do it. 30 degree entering water, go over to our pressure drop, and that'll tell us what our GPM is. Again, pressure in minus pressure out, and we do the math. Here in this example, 40 in, 36.6 out, so 3.4 pound pressure drop at 30 degrees, 7 GPM. So that's the minimum flow rate for a closed loop system. Temperature difference, I'm pretty sure you guys can figure that out. Temperature in, temperature out, do the math. So here in this example, we've got 36 degree entering water temperature and 31 roughly out. So what mode of operation? This is a source heat exchanger, so the water coming in is warmer than what it's leaving. So that warmer water, we're picking up heat from that 36-degree water and putting it into the refrigerant circuit and leaving at a colder temperature. So in this example here, we are in heating mode. In heating mode, water in is always higher than water out. In cooling mode, water in is always cooler than the water going out. Here in this example, we've got a 5.6 temperature difference. So here's an example of our heat of extraction. If we know we've got 7.2 degree temperature difference, we've got an entering water pressure 52.4, leaving at 47.6. So you have a 4.8 pressure drop. So we're going to tell you here in this example that 4.8 psi pressure drop at 50 degree entering water temperature is 12 GPM. So if we know our temperature difference and we know our GPM and we know if we have antifreeze in the system or not, then we can do the math. So we just do the math. It'll tell us 41,900 BTUs. That doesn't really tell us a whole lot. I mean, it tells us what the unit is doing, but we need to go back to the manual and compare it what's in the manual. We always need to be within 10% of the heat of extraction or rejection from what's in the manual. As long as it's within 10%, there's no need to put refrigerant gauges on, no need to do anything else. We'll just have to, it's running fine. There's no need to put the refrigerant gauges on there. So in this example, the book would tell us that it should be 40,100 BTUs. So yeah, we would be within 10%. Now, normally we're not going to be, unless maybe we're moving a little bit less GPM that's really stated in the book or something like that. Normally, we're not going to be a whole lot above what's in the manual. So if you're way above what's in the manual, you may need to rethink your calculation and look at it again. So we'll go through a few practice exercises here today. Here in this, we're going to assume that we've got 1600 CFM, and obviously we're in second stage. Here it's a YT packaged unit. We're using methanol as our antifreeze. So the first thing we're going to do, and it doesn't matter to me whether we check temperature difference or pressure drop first. We're going to have to check both, so it doesn't really matter which one we check first. We're going to check pressure first here. We've got 49 PSI in, 46 out. So we do the math on that. That gives us 3 PSI pressure drop. Take our entering water temperature at 53.5, and we're leaving at 44.6. So that tells me our water temperature is higher coming in than what it is leaving. So we're extracting heat from the loop field. So we're in heating mode. In this example, we've got about an 8.9 degree temperature difference. So we know we're in heating. The brine factor for methanol is we're going to use 485. Anytime we're using antifreeze, we'll use 485. We had a pressure drop of 3. Again, that's not GPM, so we'll have to go back to the manual here. We were at roughly 50 degree entering water temperature, and we had a 3-pound pressure drop. So at 2.9, that's 9 GPMs. That's pretty close to where we are. So we are at 9 GPM. Now that we know that, we know our temperature difference. So we run the formula, 9 GPM times our temperature difference of roughly 9 times our brine factor, that 485, because we've got antifreeze in the water. So 9 times 9 times 485 equals roughly 38,848 BTUs. So we need to take that 38,800 and compare that what's in the manual. Again, 50 degree entering water, 9 GPM, and we had 1,600 CFM. So we go to the HE, follow that down, and that tells us 39,000, that says 39.6, so 39,600 BTUs. So as long as we're within 10% of that number, we're at 38.8. The book should be at 39.6. So as long as we're, under about or over about 36,000 BTUs, we're within our 10%. So with this calculation, yes, the unit is operating properly. We'll go through another one here. Now we've got a 5-ton packaged unit, 1950 CFM, and we're in second stage. Now we're just running straight water. So more than likely we're on a open loop system or a pump and dump or however you want to call it. But we're pulling water out of the ground and putting it back down a drain or back outside. We're not reusing that water. So we'll look at pressure drop, 23.5 in, 21 out. So a 2.5 pound pressure drop. Entering water temperature of 48.7, and we're leaving at 67.9. So the water temperature coming in is less than the water going out. So we're picking up heat from the home in the refrigerant and carrying it back outside, and more than likely dumping this water, but we're not, we're rejecting that heat outside. So we've got 19.2 degree temperature difference. So we're in cooling mode, and we're using straight water. So there is no brine, there is no antifreeze in the water. So the brine factor for straight water is 500. We had a 2.5 pound pressure drop. So we can look in the manual at 50 degree entering water temperature, 2.5 pound pressure drop. That should be on pressure drop, not feet ahead. Sometimes when I switch these over to the widescreen, they'll miss their mark. So I'm going to make a note so I can change that. So 2.5 pound pressure drop is equal to 7.5 GPM. So we know our GPM, which is the recommended flow rate for an open loop system. We had a 19.2 degree temperature difference. So now we've got all the numbers. We can run the calculation. 7.5 GPM, 19.2 temperature difference times our brine factor of 500. I think that'll give us like 72,000 BTUs. So we need to look in the spec manual again. 50 degree entering water, 7.5 GPM. And we were at 1950 CFM. So we take our heat of rejection in this one, not heat of extraction, heat of rejection. It actually is 80,000, should be up just a little bit more, 80,400 BTUs. So we're at 72,000. 10% of 80,400 would be 72,040 BTUs or something like that. So as long as we're within 10%, which we are barely, we're like right on the button at 10%, that it is operating properly. Now, if you get one that's really close on the line like this, maybe you're moving a little bit more GPM than the 7.5 GPM, or maybe there is starting to be an issue. You'll have to kind of look at why you're here on this job. Did you just come out to do a preventative maintenance? If so, I really wouldn't do too much. I'd probably make a note on your ticket to check it again, in 6 months or so, and make sure that it hasn't gotten outside of that 10%. If it's not keeping up for some reason, then you may want to dig into a little bit deeper, but normally we don't size units that tight. So hopefully it's not because it's not keeping up. If that's the case, we'll have to dig into it a little bit deeper. But hopefully, we can just wait in 6 more months. It'll just, roughly be the same. Hasn't dropped anymore. But I definitely, in this situation, make a note on your ticket to double check that again later on down the line, 6 months or so. We'll go through another one here. Now we've got entering water pressure at 18, leaving at 15. So we got a 3-pound pressure drop. Entering water temperature of 30 and leaving at 26.9. So we're extracting heat, so we're in heating mode. Now, as you do a lot more geothermal and you see temperature differences, you'll start to notice, hey, something doesn't seem quite right. Now, again, if your flow is outrageous and you're moving double the flow, your temperature difference will be a lot narrower. But you'll start to notice temperature differences and say, 3.2 degree temperature difference seems kind of narrow. If my GPM is fine, then we probably got an issue. Normally on a closed loop system, when we're running 3 GPM per ton, we're normally about 8 degree temperature difference, somewhere in there. On an open loop, when we're running 1.5 GPM per ton, we're about double that, so about 16 GPM. So you can kind of remember that and kind of look at some of your temperature differences. So here we do have antifreeze in this system. We're in heating mode, so our brine factor for glycol is 485. We had a 3-pound pressure drop at 30 degree entering water temperature. So if we look, 30 degree entering water temperature and roughly a 3-pound pressure drop would be our 9 GPM. So we know our GPM, our delta T was 3.2. So now we can do the math. 9 GPM times 3.2 temperature difference times our 485. That equals 13,968 BTUs. So we can look it up in the spec book again at that 9 GPM. I believe we were at 1240 CFM. So we look at the HE, the heat of extraction. It tells us 22,700 BTUs is what we should be outputting on that unit. So 10% of 22,700 would be roughly, we would be about 20,000 BTUs. So we're at roughly 14,000. The book is at 22.7. So no, we are not within 10%. Now, when I look at this, and I've been doing geo for quite some time now, when I look at this number, I look and say, well, I'm running about 2/3 capacity of the unit. So when I think about it, when you're in first stage compressor, it runs at 2/3 capacity. So it could just be that for some reason you're not in second stage. When we run first stage, second stage, it doesn't cut it in half. We run 2/3 capacity first stage, and then the other third kicks in for a second stage. So in this example, first thing I would check is make sure it's in Y2. Make sure the compressor has a second stage call for it. If it does, make sure that it's shifting from first stage to second stage. The easiest way to check to make sure a compressor is changing stages is amp draw. It should go up usually about 3 to 5 amps based on the tonnage of the unit between first and second stage. So you can unplug the solenoid or remove the Y2 call and see if that amp draw changes. Your pressures will actually be a little bit lower in second stage than they will in first stage. Basically, that, without getting too much into the compressor today, there's an unloader when it's in first stage. So it dumps refrigerant back into the suction in first stage. And so that's why you've got higher pressures in first stage than you do in second stage. Again, I'm not going to get into the unloader today, but in this example, it's not operating properly. First thing I would check before putting my refrigerant gauges on is make sure it's going into second stage. If it is, at that point, then we would have to go ahead and put our refrigerant gauges on there, check our superheat and our subcooling, and see what's going on with the system. We do have a heat of extraction rejection video from one of our older trainers that's on our YouTube, so you can definitely check that out. Again, today's webinar will be uploaded this afternoon, so you can check it out again. You can email me if you would like a PDF of the PowerPoint. I can definitely send that over to you if you want to share it with your tech guys or whatever. But just shoot me an email, send me a call, and we'll get that squared away for you. So that's what I have today. If you have any questions, please ask. If you think of anything this afternoon, tomorrow, next week, what have you, please give me a call, shoot me an email, whatever works best for you. So that's what I have for today. I appreciate you sitting in, and we have webinars every Wednesday. So check out Enertech University, and you can sign up for those webinars. Again, all online webinars are free. So definitely check them out. And thanks again. Have a great day.